Hi, welcome back to the YouTube channel. In today's video, we're going to look at how to diagonalize a self-adjoint linear transformation. Now, if you are familiar with self-adjoint transformations, which we have discussed in the previous videos, please go and watch those videos. The link is in the description to make sure you understand what a self-adjoint transformation is. In this particular video as well, we are going to touch a little bit on that before we actually determine how to diagonalize this transformation. Okay, so let's just go ahead and get right into this problem. So the first thing that we need to find out is if this linear transformation is self-adjoint or not. And we said a self-adjoint transformation is a transformation in which t is equal to t star, where t star is the adjoint of that transformation. Okay, so the first step in this process is to find the matrix of transformation relative to standard basis for R cube. So let's find that matrix of T relative to what? Standard basis for R cube. And the standard basis are basically E1, E2, and A3. Okay, good, cool. So what's the next thing? So the next thing is first, I mean, basically we need to find the matrix, right? So the next thing is we need to find T of each of this. So this is T of E1. So we need to find T of E2 as well as T of E3. Okay. Now I just want you to pause the video here and quickly try to calculate what T of E1, T of E2, and T of E3 are. In the next second, I'm just going to give the answer. So you can pause the video right here to determine that. Okay, good. So let's just go into it now. So T of 100 is basically 0, 1, 1. T of 0, 1, 0 is just basically when y is 1 and the rest are 0. So we have this. And the last one, oh, sorry, I already have equality. And finally, T of 0, 0, 1 when z is 1 and the rest is 0 is this. Okay. Now, the matrix of this relative to standard basis will just be writing the rows as a column vector for this matrix, right? So the second row will be the second column here, which is 1, 0, 1, and the third one will be 1, 1, 0. So this is the matrix of transformation relative to standard basis for T. Okay. Now, when you look at this, you quickly observe that A is symmetric. When this happens, this basically means T must be equal to what? T star, which implies that what? T is self-adjoint. Okay, very cool. Now, let's talk about the theorem, which is the spectral theorem for linear transformations. And what this theorem says is when we know that what T is self-adjoint, we will know this to be true. If T is self-adjoint, this implies that what we can diagonalize T is diagonalizable. So this basically means that the transformation that we have up here that we are discussing, that is under discussion, is actually diagonalizable. So now we will go ahead and diagonalize it. Now, if there were a couple of videos, probably a video that I made before that explains how to diagonalize a matrix or a transformation. You can go right into that video and also watch that in relation to the method we're going to use to solve this particular problem. So they're basically the same thing. So now let's go ahead and diagonalize this. Okay, it's going to take a while, but just be patient. Let's get through this problem together. Now, the next step is to diagonalize. And what this basically means is we need to transform this matrix into a diagonal matrix. Right? This is what it means to diagonalize. We're going to turn this into a diagonal matrix where E1, E2, E3 will be the eigenvalues, right, for the transformation, and correspondingly would obtain three vectors B1, B2, B3, and this will be the eigenvectors corresponding to this eigenvalue. So this will be corresponding to E1, E2, and this will be corresponding to E3. So basically, this is what you need to do, right, in order to diagonalize these metrics. Now, how do we do that? So the first step in this process of diagonalization is to find the characteristic polynomial, right? We need to find the characteristic polynomial first. And this is basically the determinant of this A matrix minus Ti. And what this means is we need to just find the determinant of the matrix where we subtract T from the diagonals of this A, right? So this is going to be 0 minus T, 0 minus T. So we have minus T again, 1. And the last one we have 0 minus T. I hope this is making sense so far. So from here, what do? We find the determinant of this. And we have to be very careful in order not to make mistake because we have 3 by 3 matrix. So how do we find the determinant of this? It's just the first. So if you look around, you need to find the column or the row that will be easy to find the determinant of, right? But when you look at this matrix, all of them are complicated, but there's no easy way out. So we just choose the first row. Okay, we'll just focus on this first row. So which means the first term of this determinant would be minus T, which is the first entry, multiplied by the determinant when we close the row and column it belongs to. So that will be minus T, 1, 1 minus T. Minus the next term, which is 1, okay? So we are going to have, there's going to be alternating signs. So the first one has plus, second one has minus, the third one will have plus, the fourth one, if there is, would have minus, and so on and so forth. So the second one would have minus, then the second entry, which is 1, so let me just put bracket around it, multiplied by the determinant. If I close the row and column that belongs to 1, so that will give me, I'll close this column, so that will give me 1, 1, 1, 1 minus T. And finally, I have plus the last entry, which is here, last entry, which is 1, put bracket around that, multiplied by the determinant of, if I close the row and the column this one belongs to, so I'll have 1 minus T, 1, 1. Okay, so this is what I need to determine. So the next steps are probably very intensive in terms of trying to figure out how to simplify the expression, but I'm sure we'll get through it together. So this what will happen next is we have minus T. Determinant of this is basically, so let's have a big bracket, minus T times T. So we multiply this minus multiplication of this. So minus T times T minus T, that is T squared. Then minus 1 times 1, 1. So the next one, we have minus 1 here. 1 times minus T, we have minus T, minus 1 times 1, which is 1. So be very careful with the signs. Then plus, we have 1 multiplied by 1 times 1, which is 1, minus 1 times minus T, which is minus T. Okay, so let's simplify this. So we have minus T. Now, this is difference of 2 squares, so we can expand this to be T minus 1, T plus 1, okay? Then for this one, we can see that when we multiply through by minus, we have plus minus 1 times minus T, that was plus T, minus 1 times minus 1, that is plus 1. So we have this. And finally, in the last one, we have 1 times 1, which is 1, and then minus times minus T, which is 1 plus T again. Okay, so let's just so now we can observe that what T plus 1 is common to all the 3 terms, so we take T plus 1 out. So what will be left here is minus T times T minus 1. What is left here will be 1. What is left here would be 1. So let's just put this together. We have T plus 1. So expand this, we have minus T squared plus T. Then 1 plus 1 is 2. Okay. Now, notice also that we can take minus out of this. So it's always nice to write a quadratic expression with the coefficient of the quadratic term. So with the coefficient of T squared to be positive, right? So we take the minus out so that we can have T squared, and the other signs will change inside. Okay, we have this. So we can now factorize this. This is easily factorizable as what? T minus 2 t plus 1, right? So basically our characteristic polynomial is this. This was quite long. So it's going to be square minus this. So we observe that what? One of the factors has an algebraic multiplicity of 2. So this factor, so let's look at the eigenvalues first, then we'll talk about the algebraic multiplicities. So the eigenvalues would be the root of this characteristic polynomial. So which means our t will be what? Minus 1 and what? 2. And t of minus 1 will have algebraic multiplicity of 2, and this one will have algebraic multiplicity of 1. Why? Because the powers of each factor here of this factor is 2, and the power of this factor is 1. So those will determine the algebraic multiplicities. Now, for us to be able to, remember we said we can diagonalize this. We've already concluded based on spectral theorem. Now, what does this give us? It gives us that it allows us to conclude that what? We must have also the geometric multiplicity of this eigenvalue must also be 2, and the algebraic and the geometric multiplicity of this one must also be 1. Now, there is no way, if you are solving this problem and you find out that what the geometric multiplicity is 1, that means that there's a mistake somewhere in your solution. So because you have to be sure that the geometric multiplicity has to be 2, because we know this transformation is diagonalizable. I hope that makes perfect sense. So now, what's the next step? Okay, we found the eigenvalues. So the next step is to okay, we're in the fourth step now. So the next step is to find the eigenspaces of each eigenvalue. So now when t is minus 1, we need to find this eigenspace, which basically means we need to put t as minus 1 in this matrix that we have in this matrix, right? Let's not forget, in this matrix. So when t is minus 1, let's look at that. What does that give us? So this gives us the first one to be minus 1, that is 1 1 1. The second one too, we also have 1 1 1, and the third one we have 1 1 1. Remember, we're just substituting t as what? Minus 1 here. Now this gives us the coefficient matrix of a homogeneous system, right? Where these are the variables. So this gives us x times 1 plus, for the first one, we are going to have basically the same thing, the same equations for each of the rows, right? Each of the rows would have the same coefficient, and so we have the same thing. So this means that what? X plus y plus z must be equal to 0. Now, this basically means we have two variables here, two free variables here. So we can solve this in terms of x, and x will be minus y minus z, where y and z are the free variables. So now let's look at the solution set. So this solution set means x is minus y minus z, y is a free variable, z is a free variable. And when we write this, we now try to separate this into vectors that contains only y and vector that contains only z. Okay, so what this means is we can separate this into minus y, the last component is 0 because there's no y in the last component, plus the vectors that contain only z. The first component is minus z, second component would be 0 because there's no z in the, you see there's no z in the second component, and the last component is z. Now that we've done this, we can take the y out and have this, take the z out, and we have this. So therefore, the eigenspace for the eigenvalue minus 1 would be spanned by this vector, these two vectors. So you see the geometric multiplicity is 2. So geometric multiplicity means the number of vectors that will span the eigenspace of that eigenvalue. And in this case, we have two vectors. So these two vectors would constitute the um, the geometric multiplicities, which would give us two vectors, right? So the geometric multiplicity of this eigenvalue is 2. Now we go into the last one, which is when t is equal to 2, and we also try to solve this. Now when t is 2, what do we have? When t is 2, what do we have? So we basically have, we put 2 into this matrix. What does that give us? So we have, so just to be sure, so we got t equal to 2 here. So that would give us minus 2, 1, 1. We have 1 minus 2, 1. We have 1, 1 minus 2. Now, when we solve this again, this means minus 2x plus y plus z equal to 0. This means x minus 2y plus z equal to 0. Remember, this is the coefficient matrix of a homogeneous system. And what it means homogeneous means that on the right-hand side are all 0, okay? And then we have x x plus y minus 2z equal to 0. Now, when we look at the first and second equation, we can add, we can basically subtract. So subtract equation 2 from 1. So when we do that, we see that what we have minus 2x minus x, that will give us minus 3x. Then we have y minus 2y, so that will be plus 3y. Then z minus z is 0, equal to 0 minus 0. So this implies that what 3x is equal to 3y, which means x is equal to y. So we have x must be equal to y. Perfect. Now let's substitute this into the third equation here. Now, when x is equal to y, that means 2x, that means x plus y will become 2x minus 2z equal to 0, which means what? 2x equal to 2z, which means x must be equal to z as well. So basically, we have x equal to y equal to z from this particular set. Okay? So this is what we are getting, right? Now that we have the, what does it mean for our solution set? X, Y, Z, everything can be written as what? X, X, X. Okay, because X equal to Y equal to Z, right? And then we can take X out, so that we have this. So that means for this agent space, it will be spanned by this vector 1, 1, 1, which is an algebraic multiplicity of 1. So therefore, our set of this we call, remember we call it B. Our eigenvectors for this diagonalization would be, so let's take a look at all of them. That would be minus 1, 1, 0, minus 1, 0, 1, and finally 1, 1, 1, right? And therefore, our diagonalized matrix would be the eigenvalues being here. So we have minus 1, we have 2 minus 1s, and the final one, 2, where the other is are 0. Now, this means, what does this mean? This means for this transformation, relative to the standard, not standard basis now, relative to this basis for R cubed for both the domain and the range, our matrix of transformation will now be this diagonal matrix. That is what it means to diagonalize. And we're going to use this concept in the later videos when we talk about quadratic functions. So that will be the end of this video. Thank you for staying to the end of this video. Please like and subscribe, and comment down below if there are any video requests that you'd want me to help you with. I'll be more than glad to do that. So if there's any other thing, send me an email, shoot me an email. My email is down in the description as well. So see you guys in the next video.